Okay, let me check if I can. Okay, so this is the title of my talk. In this talk, as you see, we will have two, let's say, main actors. The first is coarsening, and the other one is percolation. So let me. Then the problem will be to see how they can coexist. I will explain what I mean by that. So, okay, let me just say a few words about. Of course, all of you know both coarsening and percolation. We heard already. But let me introduce them with few words. Coarsening is what you get, for instance, when you mix two liquids, like, I don't know, oil and vinegar when you prepare your salad. And then if you leave them alone, after some time they phase separate, which means that they form domains. If oil and vinegar are in the same amount, the morphology is the one you see in this picture. And what happens then, these domains, they grow, they coarsen, until a complete phase separation occurs. This is a thermodynamical phenomenon, so this is driven by minimization of some thermodynamical potential, free energy. And you can see that interaction between molecules is an essential ingredient, of course. This interaction gives rise to correlation, which builds these domains. And okay, it's an instance of non-equilibrium dynamics. And you can also check that these domains, they are not fractal. They may seem a little bit strange with some holes, but they are not fractal. Then I want to compare this problem with percolation that we heard already a lot about. So in this picture, this is a percolation cluster at criticality. And these are the properties of percolation. It's a purely geometric problem, non-interacting, no correlation by definition. When I talk of percolation, I will refer to standard percolation, which means random percolation. It's purely static, and this is, of course, a fractal. So if you compare the properties of this system with this one, you see that one by one, they are exactly the opposite of the other. So this is, you have free energy, you don't have free energy, it's interacting, this is non-interacting, this is correlated, non-correlated, and so on. So in the first part of this talk, I will give a brief introduction to these two problems, and then in the second one, I will try to show you that although you may not expect to see percolation in coarsening, because the properties are very different, actually what happens is that almost any time you have coarsening, you also have some percolation effect. In some sense, this picture here is contained here, in some sense, although you cannot see clearly by eye. But this is what happens. Okay, and I will focus on two dimensions, of course. Okay, so let me mention my collaborators on this, which is mainly people in Paris, Letizia Cugliandolo, Marco Pico, Thibaut Blanchard, Ferdinando Insalata, who is a student of mine, now in London. And there is a lot of other people working on this subject, among which our dear organizer, Jeff. Okay, there are some papers that you can look at. Okay, these are some examples of phase separation. So let me start now with phase separation or coarsening, if you want. This is what happens in a mixture of two glasses. These are two different glasses. This is an experiment. You see, initially they are quite mixed, and then they demix by formation of these clusters, which grow. This is a small film which shows phase separation of two kinds of lipids. And this other example this is a model, not an experiment, is a model to describe phase separation in a binary liquid, like vinegar and oil, let's say. But this is the morphology I will be mainly focused later. Okay, so in order to describe coarsening, I will use the most simple terminology, which is the one in my magnetic system, because of course if you have a magnet, okay, we all know that you have a high temperature phase where everything is, let's say these are Ising spins, up and down. So at high temperature, they are basically uncorrelated. At low temperature, they point in one of the two possible directions. And coarsening occurs if you prepare your magnet at high temperature and then you quench. So what you have is formation of domains and coarsening of domains. This is something that is very well understood, both from the static point of view and also the dynamics is very, very well understood, although we don't have a, 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 The model, of course, that we can use is the Ising model. This is the Hamiltonian, and then you supplement it with some dynamics. And for instance, if you do numerically, we can choose this non-conserved dynamics, which means that you take a spin and you flip it with some transition rate. In the following, we will consider the case where you prepare the system at infinite temperature and you quench to 0 temperature. This is because it's simpler, but basically nothing changes if the initial temperature is not exactly infinite and the final one is not 0, provided they are one above and one below the critical one. Okay, so look at the first stripe here. So this is what goes on in this model. When you quench it, you start from a disordered state, and then you have formation and growth of these domains. The other lines are different models where you also have coarsening. So let me mention one thing that will be important in the following. In all this coarsening process, at all this time, the magnetization, which means the difference between the red and the white spins, up and down spins, is fixed to 1/2. It doesn't move from there. So in some sense, you don't have complete phase separation in this picture. You have complete phase separation, which means oil on one side and vinegar on the other one, only when a finite size effect intervenes, which happens later. At some point, coarsening will stop and we'll have something different. But as soon as you have coarsening, the magnetization, which means the number of the two kind of spins, is constant and is equal to 1/2. Okay, during coarsening, you have a property which is called dynamical scaling, which basically means that if you take configurations at different times, like here, they are equal, except from the fact that the size of the domain grows. Of course, this is true in a statistical sense. And the size of the domains usually grows in an algebraic way, usually with an exponent 1/2. Okay, so this is dynamical scaling stated in a somewhat more elegant way, which means that there is only one length scale which is relevant, which is this L of t, namely the size of the growing domains. Of course, this has consequences on observable quantities, like correlations. For instance, G is the equal time correlation between two spins at distance r, on two sides at distance r. Due to dynamical scaling, this function, which in principle is a function of distance and time separately, it becomes a function of the ratio between r and L of t. And this m squared in front is a constant. And this is true also for other instances of correlation function like this one, which is at different times. So this means that as time goes on, the correlation as a function of r, it spreads, the correlation spreads, but if you plot it as a function of r over L of t, you get collapse on a single curve. So this is how you can check dynamical scaling. Also, you can notice that if you interpret this small t, which is time, as capital T, which is temperature, and that L of t like a coherence length, and you replace this constant by some power law of the distance, you get the usual form of scaling in usual critical phenomena, where you have that t, small t, or to be more precise, 1 over t plays the role in the coarsening process of the distance from a critical point, exactly as t minus tc is the distance from criticality in static critical phenomena. So this is something reminiscent of equilibrium scaling. So this is, this is a simulation. You see this correlation function I was talking about, plotted against r over L of t, and you have to look to this lower bunch of curves. You see that this is measured during coarsening at very different times, and you see that you get a very good collapse. So this is dynamical scaling. So from dynamical scaling, we learn some things. So the first is that the domains are not fractal. Why? Well, because if I go back, remember that in usual scaling, you should have this power in front. This power is there because this exponent is related to the fractal dimension of the domains. In coarsening, you don't have it, or if you want, this exponent is 0, which means that the fractal dimension is equal to the Euclidean dimension. So these are not fractal. And then, of course, the kinetics is driven by interaction, which builds this correlation, which spreads over larger and larger distances. So this was coarsening. Now let me present a brief introduction to percolation, just to fix the notation. So we want to compare percolation to coarsening, so we stay on the same lattice, for instance, the square lattice. And then we occupy independently with a ball, which means that we, in the spin language, we put a spin up with probability p, or a spin down, which means that it is empty with probability 1 minus p. In this problem, of course, the correlation are 0 by definition. Okay, when you put this particle, you form domains, as we know, and some domain may happen to percolate, which means to go from one side to the other one, like the green one here. And we know that in a large system, this occurs at the critical probability, PC, which on the square lattice is 0.59. And this is what happens. So in this picture, white are empty sites, and gray and black are filled with particles, and the black ones are those which belong to the percolation cluster at criticality, which, of course, as you can see, is a fractal. Okay, there are some quantities that percolation community usually look at. The first is the perconnectedness, which is the probability that if you take two sites at some distance r, they belong to the same cluster. If you are at criticality, it is well known that the behavior is algebraic with an exponent which is exactly known. And this is the result of a numerical simulation. You see that this algebraic behavior is very well reproduced, except here because you have finite sites, because this is a simulation. Another quantity that I will look at is the winding angle, which means the following. So take a cluster of percolation and 2 points on the frontier of this cluster, and draw the tangents in these 2 points to the structure, and then measure the angle, for instance, counterclockwise between these two tangents. This is the winding angle. On average, this angle, of course, depends only on the distance, which is the distance along the perimeter between these P and Q points. And at criticality, there is this exact results, which says that the square winding angle, on average, grows logarithmically with a constant k here, which is known is equal to 6 for random percolation. Okay, another thing that we know is that when you are at PC, you have spanning of a cluster, but it can span in different ways. For instance, it can span horizontally or vertically, like in those schematic pictures. And this is a realization where you have spanning vertically. And this occurs roughly 1/3 of the time, so with probability around 1/3. Or you can also span both in two directions, like in this picture here, horizontally and vertically, and this occurs with probability a little bit less than 2/3. Or you can span diagonally, like there, with a small probability, 0.04. And then, depending on boundary condition, you can have also more exotic spanning, like winding several times if you have periodic condition, but the probability of those is very, very small, so we will neglect it. Okay, so now let me come to the main question of this talk. If there is percolation in coarsening, in which sense? Well, I look at the domains of spins, like this one, and I'm asking if this picture here has something to do with this one. So the naive answer, at least to me, is no. Why? Because, okay, the initial state of coarsening is an instance of random percolation, because spins are drawn randomly, side from side to side, but the probability is 1/2. So 1/2 is not enough to have a spanning cluster. So initially, we don't have a spanning cluster, we don't have critical percolation. The following evolution, as I said before, keeps m equal to 0, which means keep p equal to 1/2. So again, I would conclude you cannot have anything spanning in the sense of percolation. And also, the following evolution builds some correlations, and correlation is, in some sense, an enemy of random percolation. So very naively, I would answer no. Okay, but now I'm trying to convince you that actually the opposite happens. First of all, we can look at configuration. So if we look at configuration, so this is the simulation. This is the initial configuration of my coarsening system at time equal to 0. Then if you go on with time, you see that very early you have the formation of a spanning cluster, which, however, is unstable. It disappears after some time. Then you have another one spanning vertically, growing. And at time, here something important happens. At time around 4, you have the formation of this blue one, which spans horizontally. Then you will see that the black one disappears. The blue one remains there. And if you go to much, much longer times, like more than 100, you see that the blue one is still there. It changes a bit, of course. It is coarsening, but it is still there. And if you go to virtually infinite time, you get to this situation, which is obviously is the product of that one. So what we see is that there is a formation of a permanent spanning cluster, which remains forever, at a very early time, like 4 Monte Carlo steps. So this is so in some sense, the fate, this is the title of a paper, the fate of the Ising model is decided very, very early. So you will reach the final state after 1,000 of Monte Carlo steps, but after 4 Monte Carlo steps, you are already, the destiny, the fate of the model is already sealed. Okay, this is a spanning cluster. This doesn't mean that it is one of percolation, of course. So in order to check that, we can look at several things. For instance, crossing probabilities. Remember that I showed you before that in percolation, you can cross in this way, and this way with probability 0.62, 1/3, and 0.04. So during coarsening, we can check which is the probability at any time to observe one cluster which spans in one of these 3 different ways. If you plot these probabilities as a function of time, you get these 3 curves. This is double crossing, vertical, and horizontal, diagonal. So you see there is a transient, but after some time, they go to some asymptotic values. And the interesting fact is that these asymptotic values are exactly the one of random percolation. In fact, you see it is 2/3, 1/3, and 0.04. So this already tells you that these spanning clusters, they probably have something to do with random percolation. But okay, if you're not convinced, we can look to something else. For instance, the perconnectedness functions. This is the perconnectedness function during coarsening. So first of all, the black one is the picture I showed you before, which is for percolation. And the colored one are the perconnectedness function measured during coarsening at different times. Times, you see, are here. So this is an early time, and then the red, and the violet, and so on. So what you see here, that apart from a vertical shift, which can be explained, I don't have much time to go into that, but it can be understood. You see here exactly the same slope of random percolation, and also the same finite side effect. Except that this is true only for distances which are larger than some critical distance or typical distance, which is marked by this red dot, which as time goes on increases. Okay, but beyond that length, you have what you would expect for percolation. Okay. Also, you can look at the winding angle. So remember that in percolation, you have this logarithmic behavior with k equal to 6. And if you measure it during your coarsening, you get the following. So this dashed line is random percolation, and these curves are in coarsening at different times. So again, you see that apart from a shift, as before, you have exactly the behavior of percolation. Indeed, you can fit this constant k here, and it turns out to be almost 6. And again, also you see here you have this. This is true only above some typical length, and so we can ask what is this length. And okay, if you assume scaling, there is only one length in our problem, and so this length is L of t. And in fact, it makes sense because For distances which are smaller than L of t, everything is correlated, so you cannot have percolation. But for larger distances, the behavior is the good one. Okay, another thing that you can see is that this percolating object that is present in the system, as I said, it is not there initially, and then at some point it touches the boundary. So this means that it grows. It also is grown. So the picture is like more or less the following. At each time, you have domains growing, and their typical size is L of t, but you also have this other growing object, which is the percolation class, which I couldn't represent in a better way than this one. And this is also growing, and it grows much faster than the domains. So very soon it hits the boundary. Okay, but this implies that dynamical scaling must be corrected, because dynamical scaling, remember, is the fact that you have only one lens in your problem. Here you have two. And in fact, you can check that dynamical scaling, if you look very accurately, if you do accurate numerical simulation on the left part of this picture, you can appreciate that, as I said before, that if dynamical scaling is true, when you plot against this quantity, you should get a perfect collapse. And actually, you get here, but this is not very good here. This is because you have this extra lens, L of p, which I was talking before. So dynamical scaling must be corrected in order to keep track of this second lens. It can be done. So you can. It turns out that if you want to have collapse, you have to use a system of different sizes. If you do that, there is a way to do that. I cannot enter into details. You see that the collapse is, again, very, very good. Okay, so this is the true way of scaling your data, if you want. Okay, so next question is how general this phenomenon is. It's rather general. So for instance, you can check that you can choose different lattices. We checked all these, one and others, and still you see the same phenomenon with the same properties, more or less. Also, you can change periodic boundary, you can change boundary conditions, and it doesn't matter much. You can change the dynamics. As I said at the beginning, the picture I showed before are for what is usually called non-conserved order parameter, which means that you pick up a spin and you flip it. This is what happens in a magnet. So you pick up that red spin and you flip it. It doesn't flip, but okay, it flips. But this is for magnet. I mean, for binary liquids, you cannot flip a spin because that would mean that you transform a vinegar into an oil, which you cannot do. Water into wine, there was a guy which was used to do that, but not vinegar into oil. So if you want to introduce a dynamics here, you have to do Kawasaki spin exchange, which means that, okay, you have to reverse a couple of spins, which means you exchange water and oil, vinegar and oil. Okay, but if you try with this new dynamics, again, you see basically the same. I'm trying to go ahead, okay. Also, you can check with different models, like the water model, which I don't have much time to go into, or with the addition of some quenched disorder. So you can take your Heising model, this one, and you can let your coupling constant to be random. Of course, random, but still ferromagnetic, because you want coarsening. With some distribution, for instance, that flat distribution there, without frustration, of course, or you can add some random magnetic field with some distribution, for instance, by model, and you can check with these these disordered models if the same percolating structure happens to be there. Before saying that, let me say that when you had even a small amount of this disorder, the dynamics changes abruptly. For instance, so you see in this picture, the black one is the system without disorder. Here, this is the side of the domains, which grows algebraically like t to the 1/2. As soon as you introduce a small amount of disorder, everything changes. And you can check that these curves, for long times, they become logarithmic. So a small disorder has a strong effect on the dynamics. But despite this, if you look at the things that I showed you before for the pure system, like starting with the first one, the wrapping probabilities, the spanning probabilities, they happen to be exactly the same, provided you plot them in terms of, not of time, but of the typical size of the domain at that time. So for instance, this is the probability of spanning in both directions. And you see that the black symbols is the pure system, and all the other symbols are systems with different kind of disorder, either random bond or random field of different magnitude. And the same is true also for the spanning horizontal or vertical, and the same is true for the diagonal spanning. Obviously you get the same also for the perconnectedness. For instance, you see that you have a perfect superposition of the pure system, which is the black symbol, with all the other kind of disorder, random field, random bond, and so on. And the same is true for the winding angle, which is here. Each of these curves is a superposition of the pure system with different kind of disorder. Okay, so let me come to my conclusion. So I hope I convinced you that there is an interesting interplay between two phenomena, coarsening and percolation, which in principle, at least to me, they're not expected to live together because they have different characteristics. Well, I've shown also that this is a rather general fact. You can have disorder, you can change model, dynamical rule, it is still there. And of course, this is a phenomenon. This is something which has some consequences. One I showed you is it affects the scaling properties. Scaling properties have to be modified due to this extra length. Another thing that I didn't have time to show you is that it helps to formulate a theory of coarsening. As I said at the beginning, we don't have a theory from first principle. But of course, once you realize that there is coarsening somewhere there is percolation hidden into your coarsening system, you can borrow a number of results from percolation and use them to build a theory for coarsening, at least in 2 dimensions. Of course, well, it is expected, this fact is expected to have many consequences because coarsening is very widespread around. Okay, thank you.